Thank you very much for coming to my talk. This is the 133rd NIA CFD Seminar. And the speaker is me, Hiro Nishikawa at NIA. And I have different name, as you see here. Anyway, so today, okay. I'm going to talk about this developing an implicit gradient method for an efficient third-order cell-centered finite volume method. So, and this work has been funded by NASA. But what I really want to talk about is this. Okay. So, us versus them mentality. Okay. So you place yourself in a group with a common beliefs and values, and see other groups as enemies, and saying that the group you're in is superior. And often this is considered as something you should overcome because it can be a barrier to progress and harmony. So, and a typical us versus them mentality in CFD is this: self-centered versus node-centered, right? There has been a debate over, I don't know, maybe several decades, which is better, I don't know. So self-centered finite volume method, you have a greater resolution on like 6 times resolution on tests. Less number of face neighbors. I said there are some advantages, and node-centered edge-based scheme. Here, the solutions are stored at the nodes, and you have certain advantages here also. The flux at edge midpoint, and you have a second-order accuracy with just a simple, flux average. This is not true for self-centered. And it's stable with compact stencil, least square gradients. This is not true for self-centered. That's why you have to involve more neighbors and not just face neighbors. It's going to be unstable for tests. And economical third-order scheme for all 3 reasons. So this story that I'm going to tell today is about it's to break this self-centered, node-centered mentality and instantly resolve difficulties. Okay, I'll get back to this later. And one of the main themes I had in my algorithm research is this economical third-order methods. And I've been working on this Army Research Office project on exploring space-time hyperbolic Navier-Stokes. This is a node-centered third-order method. And on the other hand, on a NASA project, I've been working on cell-centered finite volume methods to improve unstructured grid CFD solvers. And there's a common interest between these 2 projects. That's economical third-order methods with a single numerical flux per face or edge and not requiring second derivatives at all. And this is a big deal. And toward the automated CFD with a fully adaptive tetrahedral grids. And these adaptive meshes are best with tetrahedral meshes. So we need a very accurate discretizations and efficient talk too. So in this talk, I will focus on the cell-centered method. And this third-order cell-centered method has a very unique feature where we store solutions that cell-centered, but gradients, we compute them and store them at the nodes. And this method has been already implemented in NATO Vulkan CFD codes for hypertonical simulations. And it looks very simple. Here, on the left-hand side of this equation, this is just a second-order finite volume. I mean, it's not really second order because it just has a 1 numerical flux per phase. And for triangular grid, it is second order. But to achieve third order, you need to add flux correction and the source correction. And this source correction and the flux correction, they are based on the solution gradients and the source gradients. And the source includes the time derivative too. And so this generates some kind of mass matrix for time-dependent problems. But what is really interesting here is this interpolation formula. We need to reconstruct or interpolate solution from cell center to the face center for numerical flux evaluation. But to do this, typically we need a quadratic interpolation, which requires second derivatives. But this particular scheme, this is almost like it basically looks like a linear interpolation, right? But the gradient here is arithmetic average of the grad WT, that's average over the face, gradients at the nodes. So 1, 2, 3, the nodes 3, 2, 4, right? And divided by 3. That's this one. And the other one is grad WJ is the set average this graph W1, graph W2, and 3 and 4, and divided by 4. And if you use this combination, this linear, it looks like a linear formula, becomes exact for quadratic functions. So this is the key to eliminate second derivatives from this third order algorithm. But of course, we have to we have to compute gradients, right? So typically, we compute gradients by explicit methods. For linear least squares for second order scheme, in this method, we have to compute the gradient at the node using the solutions of cells. So for linear, we just use the cells around the node. And typically in 3D grids, we have 25 cells, and that's more than enough for a linear fit. For quadratic, we need 25 is actually enough, but for robustness, we have to include more. So in this particular case, we use the node neighbor augmentation. So you use all the cells, extra cells, sharing this the neighbor cells, at least with sharing at least one vertex with this one, and that becomes this big. And then typically in 3D, it requires like 200 neighbors. That's very expensive. But the largest tensor for gradients is known to stabilize the flow solver. So by this paper. So gradients are less accurate, but you get more robustness. But this 200 is really a lot. And the implicit gradient method is a method where you compute the gradients by solving the linear system. It goes back to the Galerkin projection by Leonard, 1994. And more recently, the variation reconstruction was proposed by the group in China. And then inspired by these developments, I developed myself this implicit Green-Gauss and implicit edge-based gradient for node-centered scheme. So here, the gradient Gj at this red one is coupled with the gradients at neighbors. So you have to solve the linear system, get the gradients. It sounds like an expensive algorithm, but you don't actually have to solve completely. So you can just relax once and then update solution once. So do the iteration because you don't get the numerical solution at once. So flow solver is more stable with huge gradient stencil. Then basically implicit means your gradient depends on the stencil is huge, is the entire gradient. So, and sphere gradient accuracy is obtained, and I will talk about this a little bit, and the per relaxation cost can be lower, because here you only need to process neighbors, like 5 neighbors, instead of this many. So it can be potentially cheaper per iteration. So in this work, I want this efficient implicit gradient method for the third order nodal gradient cell-centered finite-volume scheme. And how to construct these implicit gradients. There are different approaches. One is good Galerkin projection by Leonard, 94, and the variation reconstruction. This is to define high-order polynomial in each cell and try to minimize the jump at the face, and then generate the system for gradients. And my approach is to use hyperbolic diffusion. And basically, I can extract gradient scheme from a hyperbolic diffusion scheme. I'll show you quickly here. So start with the diffusion equation. This is a simple diffusion operator. And then I write this as a first order hyperbolic system, introducing this pseudo time, put the physical time derivative on to the right. But introducing new variable P and Q, they correspond to UX and UY. This is hyperbolic, so you can easily discretize this with an upwind scheme. So you have some discretization, and you completely drop the pseudo time because you don't need them anymore. Now, what we want now is a gradient algorithm for given solution value. So I simply throw out the first equation because I don't need this anymore. What I want is the discrete equations for the gradients, P and Q. So I just leave these last two components of this residual equation. And this, if I write this as a system, this actually forms a linear system for gradients. So the unknowns, the Gj and the Gk in the neighbor, are basically the gradients. And on the right-hand side, you typically find the Green-Gauss gradient. And you can see this if you think about it, because when you do the upwind discretization, you discretize in a conservative way. And that ends up with, for these terms, you end up with Green-Gauss. And advantage of this approach is that you can introduce a lot of parameters, like a kappa from U muscle when you do the upwind discretization, and alpha G from dissipation of the upwind discretization, and the C from a source discretization, also discretization of this P and Q. And these parameters can be very helpful. And if you want a high order algorithm, then apply high order upwind scheme, and then derive high order gradient system. Okay, and if you want an economical high order algorithm, then you start with the economical high order upwind scheme. So that's the approach I've been pursuing. And so starting with the hyperbolic diffusion system, my main recommendation is to solve this hyperbolic diffusion system. And the other path is to just reconstruct the gradients from the solution. And then this leads to the alpha damping scheme that is useful for practical CFD codes. And I'm talking about this third pass. So now if you assume the solution is given, now you derive the algorithm for the gradients. And that's typically implicit. So, okay, so we are talking about here, this third pass from hyperbolic diffusion. And so in 2018, I derived this implicit Green-Gauss method for cell-centered scheme. There are two parameters, and this is linearly exact, so it can be used for second-order finite-volume scheme. But on a regular mesh, a regular hexa mesh, by taking C equals 1 and alpha G equals 1/6, this method, this implicit system, gives you the fourth-order accurate gradients on the regular mesh. And you can think about, you can actually plot this spectral property of this implicit gradient system. And 1/6 actually corresponds to a very well-known fourth-order implicit scheme. And typically it's called a compact scheme. So this is a way to, in a way, the extension of compact finite difference scheme to unstructured grids. And stability note, I haven't done any much analysis on this cell-centered version. And later I applied the same idea to a node-centered scheme. And node-centered scheme is much more interesting because it has one more parameter, kappa. And this is linearly and quadratically exact. So it can be used for third-order scheme. And the fourth-order accurate on the regular mesh, quad mesh, is the same as cell-centered on the quad. But this node-centered version achieves fourth-order accuracy on the regular tetrahedral mesh with this particular choice of the parameter. And I never expected this to achieve such fourth-order accuracy on the tetrahedral mesh, but it does. It's really interesting. And I actually, for this one, I did the stability analysis of the relaxation scheme. And there are some conditions imposed on this C, kappa, and alpha G for stability. So, okay, now. So this is what I really want for economical third-order method. On the left, typically, like variation reconstruction or other approaches, or even hyperbolic. Linear methods, I mean, system looks like this, but G, the unknown, for linear method, unknowns are gradients, so X, Y, Z derivatives in 3D. If you want third order, I mean, quadratic exactness, now you have to include second derivatives. So the system gets bigger and bigger. Okay, for quadratic, now my matrix becomes 9 by 9. And but I don't want it because I don't want to keep second derivatives. So what I want is on the right, I seek efficient algorithm, like linear or quadratic, I only keep gradients. And this is possible for node-centered edge-based scheme. So implicit edge-based gradient is very efficient. You don't need second derivatives. So the question is, would it be possible also for third-order cell-centered scheme? So that was the question I was working on. Now, and I realized that this is a cell-centered scheme with nodal gradients. So it was not very straightforward to derive this gradient system from hyperbolic diffusion scheme. But we can try to discretize the gradient equation directly. So I look at this gradient equation, G equals W. Okay, this is the definition of the gradient. And I integrate this equation over a cell and where I have the solution at the cell center and the gradients at nodes. So the integral of G is easy. It's just the arithmetic average times the volume. And the integral of the gradient, I can use third-order nodal gradients cell center finite volume without using any second derivatives. So here's the flux correction in the flux, and these are the flux, the interpolation involves these nodal gradients. So this residual is exact for quadratic functions, and without introducing second derivatives. That's nice. But it results in an overdetermined problem because I have residual at cells, but I have unknowns at nodes. And on TEDs, it's like 6 times more equations to satisfy. So that was one of the difficulties. And then, okay, so one approach is to minimize the cell residuals in the least squares sense. So define this global functional. It's 1/2 and or the sum of all cells of the residual square. And to minimize it, I just differentiate this with respect to the nodal gradients, and then set it to equal 0. Now I have a discrete equation at each node by doing this. This is one way. I don't know if there is no special reason that this is the best way or this is a good way. I don't know. I tried it, and this is second derivative free, so as desired, which is nice. But the system turned out to be difficult to solve. The Gauss-Seidel relaxation scheme diverged on high aspect ratio, and it was very difficult. And but it's worth developing this type of method because cell-centered implicit nodal gradient. Okay, this is it has the potential for being quadratically exact for arbitrary grids. The edge-based scheme, the node-centered scheme on the right, this is quadratically exact only on S. It's a very special property on tetrahedral mesh. But for this cell-centered nodal gradient scheme, it can be third order for arbitrary grids. So if we can derive a more robust nodal residual from cell residual, and it would be useful also for conventional cell-centered finite volume scheme. In conventional cell-centered finite volume scheme, you need gradients at cells, but you can compute gradients at nodes first, and then get the cell gradients by linearly interpolating or averaging the nodal gradients. So it'd be very useful. But okay, I worked very hard to make it robust. I tried to add a stabilization term like a Laplacian, but I couldn't develop a robust algorithm. And the summer conference was coming up. I had to fly to Venice, and I was running out of time. Then time to break this mentality here. Okay, so node-centered algorithm is not an enemy to cell-centered algorithm. I was thinking, only focusing on cell-centered, I wanted to develop something similar to what I did for node-centered. But, you know, especially for this nodal gradient scheme, I can try to use it, you know, whatever I already developed. And if you look at this, okay, nodal gradient cell-centered finite volume is actually somewhere between cell-centered finite volume and node-centered edge-based scheme, right? Okay, on the left, cell-centered finite volume, you have solution and gradients at cell center. And node-centered, you have solution and gradients at nodes. And the discretization, the efficient third-order scheme, has solution at nodes, cells, and the gradients at nodes. So if I can somehow transfer or recover the solution at nodes from solution at cells, I have this configuration, exactly the same as node-centered. And if I do this, then I can directly apply implicit edge-based gradient, which is nice, no second derivatives, direct, and I already have a code. So the only question is how to get the solution at nodes from the solution at cell center. And I have a way, which is this quadratic interpolation formula. So from the solution at cells to the node, to some node I can do the average. So when C goes 1/2, this is just average of cell average gradient over a cell, especially like for this one, this time 1, 2, 3 the sum of these divided by 3, which goes here. And this GI is the gradient I have right here. And if I take the average of these two and then do the linear interpolation, this is exact for quadratic functions. So when C goes 1/2, I can use this. This is a quadratically exact algorithm. I can use it for 3rd-order scheme. And when C goes 0 or 1, that would be a 1st-order method that I can use for 2nd-order scheme. Then once this is done, then implicit H-based gradient 2 means quadratically exact. No second derivatives can be directly employed. No. So the left-hand side is exactly the same as node center. On the right-hand side, you have a Green-Gauss gradient, but all you need is the node solution at node. So, and the right-hand side depends on the nodal gradients because of this interpolation. So how to solve this linear system? There are 2 approaches. Okay. So if I do this interpolation and then take the average to get the solution value at node, it would look like this. So at the center node, I have this average, averaged interpolation. And then at the neighbor is also, this is averaged. So you see on this right-hand side, it's the average of the center solution and the neighbor solution. And all this neighbor involves all the neighbors, neighbor cells around. And this one also has more neighbors. And so this stencil gets really, really big. Okay. But you can make it compact if you average the center node, you use all the cells, but for the neighbor, you only use these 2 cells. Then you can make it compact. But it turns out when I tried this, I was very excited. But the Euler solver, when I tried this, the Euler solver gets unstable with tendency boundary condition. And I still don't know why. And I hope I have a bug. But but I couldn't find a bug at that time. So I decided to go with this one. It's a larger stencil, but it's more accurate, actually, and it's more robust, it's more stable. So this was my choice. And to solve this, like I said, this right-hand side involves gradients in a huge cell. Okay, I don't want to, I can generate a new matrix, but it's going to be huge. It's not going to be as sparse as this one. So one robust way to solve it is a defect correction. So here's the update of the gradients. And this correction, delta G, is the solution of some approximate linear system. So I use this coupled system as the approximate matrix. So I solve this, apply Gauss ideal relaxation 5 times, and then update the gradients. Okay. And then get the solution at the nodes, and then compute the right-hand side, and then compute this residual, and do the iteration again. Okay. And this algorithm can be easily implemented. This node-centered algorithm is already available, and it was available in my code. So when I apply this to solve the flow equations instead of least squares, this is what I do. So starting from the initial values, gradients at 0 initially. And the flow equations, flow variables like some free stream constants. And I have to set these gradients for all 5 variables, of course. And but this is only at nodes, and the solutions at cells. And then iterate for n equals 0 to 0, 1, 2, 3 until convergence. So first thing I do is update gradients at all nodes for all variables. And by doing this 5 precondition relaxation and then update the gradient. And then once gradients are updated at nodes, I update the solution by using implicit solver. So relax this linearized residual system and then update flow solution. And then go back to gradients. Okay. So this is a loosely coupled iteration between gradient and solution. And it's not because I have to apply this 5 relaxations and also computing this residual involves a lot of interpolation. So it's not going to be as cheap as I hoped, but it's not more expensive than using processing 200 neighbors for least squares. Okay, I have some results here. So accuracy verification. So I have exact solution in a cube domain. This is a irregular Tet mesh, and I'm comparing least squares and then implicit method. And first, here's the error convergence for the solution x velocity u. And for second order accuracy scheme, this is least squares, and then red circle is obtained with the implicit method. 0 means c equals 0. So solutions, you don't see much difference, whether you use least square gradients or implicit gradients. But when you look at the gradients here, this is the y derivative. And by the way, this is a highly stretched high aspect ratio gradient. The vertical spacing is 0.0015. Anyway, the gradient accuracy is much improved with this implicit method. Okay. Oh, this is the second order implicit, and this is the least squares. And looking at third order scheme, this is the quadratic least squares here, and then this is implicit third order implicit gradients. So even in the solution, it is much more accurate. And of course, gradients are even more accurate. This is the quadratic least squares, and this is the implicit second order implicit quadratic outlet. And this is what it looks like. But iterations, when I look at the iterations, the flow solver doesn't converge necessarily fast with implicit. So in this case, implicit gradients, the flow solver took more iterations to converge. It's not much, but when you look at this solution coding, and this is the gradients actual, the y derivative. This is the least squares, and then this is implicit. I don't know what to say because it takes more iterations, but you get more accurate solution and gradients. And the same for third order. Well, it's not really clear here, but it is more accurate as we saw here. Okay, and then the Mach 3.3 is subsonic flow over smooth bump, and I can measure the spurious entropy error. Entropy error should be 0. In this case, the residual versus iteration, the second order and third order with least squares, it took more iterations to converge. And with implicit, the second order and third order, it did converge faster. And there's a similar plot for residual versus CPU time, which means that the per iteration cost is not more expensive than least squares. And this is the entropy error convergence second order scheme. And this is second order scheme with implicit. And this is the third order with quadratic least squares. And this is third order with implicit gradients. And in this case, you get more accurate solution faster. And this is what it looks like on the third grid. This is the least square second order scheme with least squares, and second order scheme with implicit. You can see much cleaner solution here. This is the entropy error controls. And the third order quadratic with quadratic least squares. And this is third order scheme with implicit gradients. So this difference can be seen here. It's much larger in the week. So I was able to develop this simple implicit gradient methods for second and third order nodal gradient cell-centered finite volume methods. So third order method remains second derivative free, which is nice, and significantly lower gradient errors by implicit gradient methods. There are a bunch of future work. The further tests, of course, needed for more realistic problems with shocks. And I'm very interested in developing Jacobian free Newton files solver with gradient added as additional unknowns. And compact sensor version, which is nice, but it was not robust. It's nice to be able to make it more robust and extend it to mixed element grids, which is possible for this cell-centered version, not possible for node-centered. And I'd like to continue to seek a more robust implicit method. Oh, yeah, I just mentioned. And maybe I can begin by constructing something like a Petrov-Galerkin upwind scheme for hyperbolic diffusion. Yeah, I didn't start with hyperbolic diffusion. That was my one thing I didn't explore. So anyway, I was able to finish this paper and present at AIAA in summer. That was great. And so we are all working towards developing robust and accurate algorithms. So we should take advantage of similarities and help each other. We're not enemies. And I like all methods, as you know, and it worked for me. So your difficult problem may be solved instantly by breaking this us versus them mentality. Thank you very much. Okay, questions?
Yeah, here, I'm assuming all the quadratic least squares were unweighted results that you showed.
Yes.
I think it's probably necessary because otherwise the boiler solvent.
Yes, for stability reason, yes.
And have you ever done any comparisons? I know it wouldn't converge if you did it, but just testing the accuracy on a fixed problem of if you do weighted least squares, meaning plot the convergence of just instead of doing.
Oh, is that the gradient?
Just the gradient itself. Because what I'm interested in knowing is if the nodal gradient method that you're using for the IEBG scheme, IEBG2, it has a nice error shift over quadratic least squares. Like all the plots you showed, it was almost a half order of magnitude, but that may go away. It may just be because from what we've seen using the nodal gradient scheme of IEBG, you doing weighted or unweighted least squares when you're building that linear system doesn't make a big difference in accuracy. So you get the same benefit as if you were doing a weighted least squares scheme using IEBG, and it's stable for both. So just kind of a comment, and if you try it, let me know if you see the same thing on the cell center side.
So for given solution, you just apply this as a post-processing?
Yeah, you can. Yeah, we've got tools that do that. It's helpful sometimes.
Yeah, that would be an interesting thing to try. Yes.
Yeah, and I think for us, when we do nodal quadratic least squares, using weighted least squares, like inverse distance weighted least squares, those plots almost overlap, meaning you get almost the same accuracy for doing a weighted quadratic least square scheme as you do using an IEBG scheme.
Oh, okay. Yeah. Okay.
What were the boundary conditions for the Gaussian bump? Were they different for each scheme? Or the tangential flow boundary conditions?
Oh, it's a no slip boundary condition using exact surface normal. And
I'm sorry, can you say that again? So I guess what did you use for pressure closure for those for the invested wall?
Well, invested wall, I use just the raw flux, and right state is defined by the flipped velocity. And here it's important to use exact, accurate surface normal to maintain third-order accuracy. And that's described in the JPP paper, 2020. Yeah, next one, 2023. So this paper describes how I actually implement this tangency condition. But basically, I use raw flux. Right state is given by this flipped velocity, so that the sum of the velocity is zero, the left and right states. Did it answer your question?
Yes, thank you.
Any other questions?
The constraint on the gradient or the normal accuracy, is that on the order property of the normal, or does it truly have to be exact in this case? Like, would you make?
It doesn't have to be exact. It should be exact for quadratic geometry. So if you fit some quadratic function over some curved geometry and then take the normal, that should be sufficient. For this one, because I have an analytic formula for the bump shape, so I was able to compute exact normal. Yes.
You mentioned one of the advantages is that you can do hybrid grids with the nodal gradient cell center.
Yes. Yeah.
Not with node-based schemes.
I don't think so. Yeah, it's a very special property on tets and triangles. But for cell center cell center method, this quadratic interpolation formula, this is the key. And this can be extended to orbital ring mesh. So I just presented a paper at the AIAA in July, the extension of this scheme to mixed element. So, and I'm continuing the development of this mixed element version of this whole scheme. Thank you.
And do you see possible to even extend that further than 3rd order, like going to 4th order?
4th order, if I'm allowed to carry second derivatives, maybe I can go further. But with gradients, just gradients, I don't know.
So you need to extend that vector solution.
Yes, or 3rd order, zero dissipation 3rd order scheme can be 4th order accurate. So minimizing, dissipations, then the scheme could be 4th order.
That's only true for for a regular grid.
Yes.
Thing,
Yeah.
because you're still relying on the grid regularity to get the cancellation at that point. If I understand that scheme correctly. This is
not this one, right?
no. I'm saying go to 4th order. For this one, it's arbitrary, meaning
Yeah,
for arbitrary elements, there's no requirement on the grid to be regular.
No requirement for smoothness of rights. Yes, yeah. So, but I don't know. I haven't tried, but zero dissipation. Usually it means 4th order, but maybe it's only true for regular grids. Yeah. But if I'm allowed to carry second derivatives, I'd be happy to explore. Yeah. Any other questions online?
How would this fit into, so for the hyperbolic scheme, for instance, you mentioned, so it, as future work, you mentioned including them in the JFK solver. Sorry, including the gradients in the JFK solver. Obviously, if it's a hyperbolic method, I understand that you have gradients in there, but when you're talking about it in this context, are you talking about in the overarching nonlinear solver or just the IEBG2 linear solver you want to do it?
Oh, this one. This, no, I'm not talking about hyperbolic. I mean, hyperbolic is an option. But if you find this implicit gradient method, working for you, already implemented, but you want more robust solver, then you can combine. Like I said, it's a loosely coupled iteration, right? Gradient updated and solution updated. No, you can combine everything into one single unknown vector, and then solve the entire residual equations together. But the covariant free Newton graph is useful because you can use this loosely coupled solver as a precondition, exactly as it is, right? Yeah. So I think that's probably one thing you can try, and you probably want to try if you have this in the code. So, and especially this is advantageous for nodal gradient scheme because on TET, the additional unknown number of unknowns is much less. Like for TETs, you have 1/6 of the number of cells because you have gradients at nodes. So extending this unknown vector is not as huge as you think. So that's it. Really worth trying. Yeah. So yeah. Good point. And there are a bunch of stuff, and I cannot do this myself. Everything.
It's something important what you mentioned about how to measure, how to compare the methods. It's not only how many iterations, it's like how to reach to this level of accuracy.
Yeah.
Exactly. Even if I need more iteration, but I'm reaching this level of accuracy, then I'm better.
Yeah.
That's how
it's very difficult. Yes, it's usual. Yeah.
Yeah, you didn't do yourself justice on this to some degree because you didn't, I think you were comparing all Bang type methods on there, meaning they're all using nodal gradients. There already is some saving for the fact that you're not doing self-centered gradient.
Yeah. Actually, yeah.
So if you had like an NN stencil, for instance, for self-centered gradients, where you had a large stencil just for linear least squares for self-centered gradients, I would imagine you would be able to show even further improvement on the conversions there. So and I think there's a lot of benefit just from the fact that you've got a whole family of schemes now
Mhm.
that are able to take advantage of nodal gradients on cell-based discretizations.
Yes, there's so many different schemes right now. Yeah. Jeff?
Hiro, I have a
Yes.
question.
Yes.
Do you see a way forward of incorporating limiters into the implicit gradient system?
Yeah, that's a good point. It's yeah, I didn't mention it here, but in principle, I mean, limiter can also be computed implicitly, or you can define some kind of residual for the limiter, and they include it in this Jacobian Newton principle, and solve everything in a simple, with a simple vector. That way, you have a truly compact finite volume scheme. Everything depends on the neighbors. And but I haven't even started to look at this. So currently we have applied limiter just like we do for least squares or anything. But it'd be very interesting to look at the way to compute limiters implicitly or iteratively. Yeah. Thank you, Chair. Any other questions? Anything? We have plenty of time. I like this. 30 minutes presentation, 30 minutes discussion.
Well, here I've got some ideas I can throw out your way. I don't have any real more questions.
Okay.
So if you're ready to wrap up, I can move to that, but I'll
Okay.
wait until.
Any questions from online?
Could you show the interior comparison?
Oh.
Again?
Yes.
Yeah.
Oh. So,
I can't really see the scale from here, but are they all scaled the same?
okay, the scale is the same left and right. These two have exactly the same scale, and these two have the same scale. So it doesn't show that the 3rd-Order scheme has a larger error. No.
Right, yeah, I just
Sorry.
wanted to check, because the plot on the right.
Yes,
Without seeing
because
scale.
I'm just comparing the least square and the implicit.
The bottom plots would be very interesting if you did it all in the same scale, I guess, and then just all blue.
Yeah, it's otherwise, I think for 3rd-Order schemes, that these entropy error levels are much lower here, so you wouldn't see it anyway. And no questions from online?
You saw implicit cases. What about viscous cases?
Oh yeah, viscous is more interesting because with nodal gradients, there's a slightly different way to develop 3rd-Order viscous scheme, and which I haven't coded yet. I have a formula on the paper, but haven't tried it yet. For viscous, quadratic exactness is not enough. It has to be cubic. And first of all, I have to do the cubic least squares. And implicit, I don't know yet. But if I have a cubic exact gradients that knows, then I can compute the viscous flux at the cell center exactly for cubic functions. And that's what I need for 3rd-Order. So I haven't tried this, but I have a formula in a note. So at some point, I'd like to try this.
In the implement, you mentioned it was already implemented in Vulkan. That one is already
Implicit. Implicit.
Implicit.
Yes.
Not only implicit. Okay.
Only implicit so far. Yeah. But there will be a viscous extension. Yes. That'll be more interesting. Development.
Which then you do not have a viscous extension, or you don't have a cubic extension for the implicit gradient system. So
Not yet.
that would be
That-
an implicit method.
Yeah, cubic. Maybe I have to introduce second derivatives.
It might be worth it. Yeah. If you decide, yeah.
We don't know.
I think at that point, maybe we look back again at the hyperbolic system. See,
Oh, yes.
that's probably a better way to do it.
Yes, so that's the advantage of hyperbolic narrow systems. Everything that works for implicit it works for viscous. Exactly the same way. But if you want to discretize second derivative operator, the conventional viscous terms, there's a different requirement. Yeah. So
Okay, so right now what you have in Vulkan is for the implicit fluxes, you have the third order. For the viscous, still gives the second.
it's second. But the current viscous scheme can use quadratic least square gradients. So it's a little bit
A little bit here and a little bit there.
yeah. So at some point, in a way, how important it is to have truly third order accuracy. You might be happy with lower second order error. So
I just had a kind of a crazy thought, Hiro, and maybe you've already thought of this. We have a problem with scheme 2 for the hyperbolic system and stability, so you came up with the CLSQ method.
yes,
To combine explicit with this.
yes,
You could in theory just replace all of that with the implicit gradient system, but that might be expensive because now you also have, it would just be expensive. I just had a thought, what if we used the hyperbolic system and we did it using, oh gosh, what do you call that? Instead of solving for like the stress or the gradients, you just do everything as far as gradients are concerned, with the frozen viscosity matrix. What's that term? HNSG, I think it was the work that you did with Hong Lo and company. So you have the gradients of that system.
yes.
You have an implicit gradient system. We know that if you use the gradients directly from the hyperbolic solution on there, that's not necessarily the most stable. What if we used the implicit gradient system as a smoother? Don't change the actual gradients in the solution, but when you're doing the reconstruction, maybe you can do that. Instead of doing an explicit combined with an implicit, stabilize it. What if we use this as a way to basically try to stabilize that scheme?
Yes, yes,
That could be pretty interesting.
yeah. I thought about it.
Oh,
Yes, that's going to be, I think, interesting. I don't know if I get a chance to try this out actually, but 20 equations for Navier-Stokes, including gradients as unknowns. This is hypothetical Navier-Stokes. But we have to compute the gradients actually for the variables.
Right.
So the gradients of the gradients. Here I use, so far I've used least squares.
Yes.
Or I can use implicit. Yes, exactly. And if I use implicit, I can add these implicit gradient system as additional residual or unknowns. Now you have, instead of 20, I don't remember how many, 6.
No, yeah, but what I'm saying, don't keep going.
Yeah, but
Don't build
that's
the ginormous ones.
yeah.
In fact, you don't even maybe need to do it for hardly any of them. What I'm saying is, if you're just using the gradients to reconstruct the primal, because or you can do the whole thing.
Yeah.
If you're doing third order, yeah, absolutely, it's huge. I'm saying let's do third order and second order, meaning third order for the implicit fluxive, third order for the primal, second order for the viscous fluxive, like you normally would do if you were doing scheme 2 or something like that. But just use IEBG to try to do it as a correction matrix. So you basically use IEBG to smooth the gradients that are going to be used to reconstruct to get to third order as a way of stabilizing it. So purely as a way of stabilizing it, not using it to get yourself to third order from IEBG, but as a way to correct the gradient variables themselves, as if you were combining them with the explicit linearity squares, which explicit linearity squares may be cheaper, but I wonder if it's less robust because we may run into the same problems with stencil sizes.
Right.
So
now I remember the Aero project, Node Central one. I'm supposed to try it. For space-time solving.
Yeah.
So
when you do, we'll see who gets there first. That's kind of an interesting thought because that was the problem that we had with hypersonic application of it was what happens when you get into the boundary layer and scheme 1 scheme versus scheme IQ, whatever the combination made a big difference, but it didn't necessarily make all the difference. So it'd be interesting. I don't know what I get because this is going to be a space-time, so it's a little bit different combination. I'd like to try to see how it works. Okay. Thank you. Yep. And no other questions from online? Okay, then thank you very much for coming, everyone. It was nice to see you.
And thank you very much for coming in person. Thanks. Okay. Bye.